Welcome back. My name is Dominic Clevey. I teach at Central Washington University. Today's lesson is on polar coordinates, introduction and graphing. Polar coordinates are something that we don't always get to see at the high school level. It's something that pre-calculus students don't always get to see. But they're a wonderful device, a really neat new technique when it comes to looking at graphing, when it comes to looking at using some sort of picture to plot lines, to plot points, to plot equations. And the basic idea comes down simply to this. If we have any sort of two-dimensional plane, the kind that we're always used to graphing on, and I plot a point, we know how to specify that point. It's almost magic in a way if you think about it, that knowing just an x-coordinate and a y-coordinate, knowing just two numerical values, specifies any one of infinitely many points on this piece of paper. One of infinitely many points on the plane. And the way we have to do that usually is we start at a certain point. We call this point the origin. We move to the right or left some number of spaces, that's our x-coordinate. We then move up or down some number of spaces, that's the y-coordinate. And the point that we end up at is the point that we want. Our question today is simply this, and it's a big question. Is there another way to do this? Is there another way to specify a point on the plane? Do we have to give its x and y coordinates? If we're really clever, can't we come up with something else? And you know I wouldn't be asking the question except the answer is yes. Yes, it must be yes. There is another way to do this. We can use actually one of several techniques, but the one that we're focusing on today is polar coordinates. How do we specify a point, and what might we do? Well, if I want to tell you where a point is on the plane, maybe the first thing I could tell you is how far it is from the origin. Instead of telling you how far it is from the x-axis and the y-axis, just how far is this from the origin? In this case, let's call this r. R is the thing that's usually used. So if I tell you that a point is 3, there's a distance 3 from the origin, is that enough to specify the point? Do you know now which point I mean? And of course not, right? Of course there are a lot of points which are distance 3 from the origin. We could even make a picture of them. But what would it look like? Yes, it would be a circle. We can plot something just like this. We could say all these points are 3 from the origin. Alright, well knowing just how far a point is from the origin then isn't enough to specify one unique point. But that's not too surprising. Even with our standard system of rectangular coordinates, our x and y, we need 2 coordinates. So maybe here we also need 2 coordinates. If I first specify a distance from the origin, what else could I specify to tell you which one? And the picture here is suggestive. You're used to the unit circle. You're used to specifying a point somewhere in the circle. And what do you usually do to specify the point? We use the angle, right? This angle, which traditionally is called theta, specifying just that angle should be enough. Now if I tell you r and theta, will this uniquely determine a point? I first tell you how far to go. Start at the origin and make a bigger circle until we get exactly r size. And now does every point in that circle have a unique angle? Yes, it does. Start on what we call the x-axis and sweep through it until we get to the appropriate angle. By specifying r and theta, by specifying a distance and a direction, we are now able to uniquely specify any point on the plane and to do it in a very new way. Let's try one concrete example. I'm going to put here the point 3, 3. 3, 3 with our old x and y coordinates. Using these, can we convert this to polar coordinates? And I have an extra dot here which I put accidentally, so let me redraw this picture. I don't want to be confusing which one I'm thinking at. Here's 3, here's 3, here's the point 3, 3. We make this in polar coordinates. What do we need to do to come up with polar coordinates? If I first draw a line from the origin to that point, I need to know 2 things, right? I need to know how long that line is, how far the point is from the origin, and I need to know this angle. Well, this is maybe not as difficult as you might expect. If I drop a line right down here, I know this is distance 3, I know this is distance 3, and so via the Pythagorean theorem, 3 squared plus 3 squared is equal to this side squared. I know this has to be 3 times the square root of 2. I also know something about theta. If we think about the opposite side, the adjacent side, and the angle, I know in general that the tangent of theta is equal to opposite over adjacent is equal to 3 over 3. And if the tangent of theta equals 1, then the inverse tangent of theta, the inverse tangent of 1, should be theta. And what's the inverse tangent of 1? Bonus points if you got it right off. The answer is pi over 4. So what do we say? We say the rectangular coordinates, and remember rectangular coordinates are the ones we've been using all of our lives. The rectangular coordinates 3, 3 correspond to the polar coordinates and we always, when we list polar coordinates, list first the distance and then the angle. 3 over 2 and pi over 4. Well, sort of nice. We started with a point that we could easily describe, and we found a new way to describe it. It would be nicer, of course, if we didn't have to do this and work through this and think through this every time we do one of these points. Let's see if we come up with some more general rules. Can we convert from polar coordinates to rectangular coordinates? And let's say relations between polar and rectangular coordinates. Probably the best way to do this is to start with a picture. Let's plot our familiar axes. Let's pick an x and a y and a point. I'm going to call this point P. I'm going to draw the same picture I had before, where this is r and this is theta. And now we're going to write down everything we can think of to relate what's going on, to relate these various quantities. And what comes to mind first? Well, maybe the Pythagorean theorem comes to mind first. This is a side length x, this is side length y, so we immediately find that x squared plus y squared is equal to r squared. What else do we know? Well, let's think about this. The length of x, the length of r, and angle theta. If we know an angle, like theta, we know an adjacent side and a hypotenuse, and we relate them in some way, yes, we're good at that, right? The cosine of an angle is equal to adjacent over hypotenuse. So I could write that cosine theta equals x over r, or the other way to write this that's actually a bit more common, is that x equals r cosine theta. Similarly, y equals r times sine theta. And we can do one more. We can do the same trick with angles and tangents we did before. We also know that the tangent of theta is equal to what? Yes, is equal to y over x. So these four, this was sort of a stepping stone along the way, these four equations are all very useful things for converting from rectangular coordinates to polar, from polar coordinates to rectangular, and we want to make sure we can go back and forth between these. So let's practice a couple quickly. In fact, let's start with something almost like what we looked at before. Let's say convert the rectangular coordinates 3, 3 over 3 to polar coordinates. And polar, remember, we're always going to write as r theta, specifying a distance and a direction. How do we do this? Well, we're going to use our formulas, right? We've already found the relationship. We know, for example, that r squared is always equal to x squared plus y squared. In this case, r squared is going to be, what is 3 squared plus 3 squared? 3 squared is 9. 3 times the square root of 3 squared is 27. 9 plus 27 is 36. And if r squared is 36, then r equals 6. It's nice when we work through the function just once, the example just once, with all the letters, because after we do, we don't have to think very hard. We can write these things down and just find the answer quickly. How do we find theta? Well, remember we know that theta is the tangent of y over x. We know y, we know x, we should be able to find this. Theta is, sorry, shocking how often I write this backwards after all these years. We know, more correctly, the tangent of theta equals y over x, and therefore theta is the inverse tangent of y over x. In our particular case, we have the inverse tangent of 3 times square root of 3 divided by 3. The 3's cancel out. The inverse tangent of root 3. You really have to know your circle, your unit circle well to get this. The tangent of what angle is equal to the square root of 3. If you think really hard, you should come up with this. If you can't, you can ask your calculator. Theta is pi over 3. And so the rectangular coordinates 3 root 3 for x and y correspond to the polar coordinates 6 pi over 3. There's simply two different ways of expressing exactly the same point on the plane. Let's try once where we go the other direction. Let's try an example where we know the polar coordinates and we want to convert them to rectangular coordinates. So let's say convert 5 comma pi over 6 to rectangular coordinates. Let's also remember we're talking about, this is all new notation, we must constantly practice it to keep it fresh in our heads, to make sure we know what's going on. Our angle is pi over 6, so from the x-axis I go up pi over 6 and I go out a distance of 5. Doing just that much of a picture should give us some hint what the answer is. Alright, we have some sense in our heads now about what x and y are equal to, and that sense will be very useful. That sense will help us keeping from making a mistake if we come up with an answer that's clearly wrong. If our x and y coordinates are negative, for example, we'll now know there's a problem. How are we going to find rectangular coordinates? These are even easier than what we did last time. Remember our formulas? X equals r times the cosine of theta, and y is r times the sine of theta. Well, we know r, we know theta, so it shouldn't be too tough. X equals 5 times the cosine of pi over 6. The cosine of pi over 6, remember cosine is the x value, so the x value of the unit circle up to pi over 6 is root 3 over 2. So I have 5 times the square root of 3 over 2. The y coordinate is 5 times the sine of pi over 6. Sine of pi over 6 is a half, so I get 5 halves. So 5 pi over 6 is the same point as, is totally equivalent to 5 root 3 over 2 comma 5 halves in rectangular coordinates. This is the first step that we need. We need to be able to understand these polar coordinates well enough that we can go back and forth between them, that we can convert rectangular to polar, that we at least know how to rename things in different ways. Let's make it a little bit harder now. Instead of just renaming a point, instead of converting a point from something to something else, let's try to convert a whole equation. So here's a challenge for us. This will be our next example. Convert the equation. Let's make it good and tricky, shall we? Let's say x squared plus y squared plus 5 times x is all equal to 5 times the square root of x squared plus y squared. That looks complicated enough. Let's convert this whole thing to polar coordinates. A little tricky to do this, but not too tricky if we remember some of the identities that we developed earlier. We know, for example, that x squared plus y squared is always equal to r squared. I know that x is equal to r times the cosine of theta. And here's another x squared plus y squared. So in fact, if we see these things right away, it gets easy very quickly. It's very important that we know our identities for this reason. So let's rewrite this. I have r squared plus 5r cosine theta is equal to 5 times what? The square root is still there. So I have the square root of r squared. But of course, the square root of r squared is something that simplifies very nicely. R squared plus 5r cosine theta simply equals 5 times r. And if I wanted to, I could even bring all these r's on the same side of the equation. The equation is no less true in this step, or in this step, or in the next one. They all say the same thing. The last one is perhaps a bit prettier. So let's try to write this. R squared plus, and what we have 5r cosine theta minus 5r. That's 5r times the cosine of theta minus 1 is equal to 0. There are lots of choices for us, lots of ways we might do this, but here's a conversion of one way of writing the equation to the other. Note here that in some sense, what we've done at this point is nothing at all. We had an equation, now we have the equation again, and we've merely translated it. What's the purpose of translation? Well, translating things makes them easy to understand. If you want to read a novel by Garcia Marquez, you could read it in the original Spanish, but it's tricky for English speakers to read it in the original Spanish. If you want to read major novels of the European Enlightenment, they are in French, they are in German, some are in Latin, some are in Italian. Nobody reads all of these languages. We translate them. When we translate them, we don't make something new, we simply make it easier to understand. There are many cases in which converting something to polar coordinates, believe it or not, I know I didn't believe it when I first learned these, makes things easier to understand. Perhaps the most famous example, the most important example, is something near and dear to the hearts of astronomers everywhere, which is planetary motion. Here's the sun. Earth goes around the sun. Earth goes around the sun in almost a circle. It's really an ellipse. It's not at all this horrible shape I've drawn here, but use your imaginations and pretend this is a perfect ellipse. What happens? Well, the distance is almost always the same. It's at least pretty close to the same. The angle changes, very importantly. And thinking about this in terms of polar coordinates turns out to make way more sense when understanding planetary motion. When we send space probes to Mars and Jupiter, even when we launch satellites into outer space, and we put the satellites up there for cell phones and GPS, we always think about things in terms of polar coordinates. There's another version of polar coordinates in 3 dimensions. I guess you can imagine that knowing just 2 might not be enough around the Earth because there's several directions to go. They're simply called spherical coordinates, and you can learn about those anytime. You'll find them, certainly in college calculus. But it's the same basic idea. Knowing these distances, knowing these angles is often a really useful thing, and we want to be able to do it here. What else might we want to do then, if we're given a couple points in polar coordinates? Well, a crucial one based on something we just said, a crucial one for things like GPS, is determining the distance between 2 points. That's how GPS works, after all. Your little GPS device needs to know how far it is to that satellite, how far it is to this satellite. Satellites might need to know how far they are from each other. Determining those distances is a really important thing. And so let's see if we can come up with that. And so our big question here, our next question is, find the distance between 2 points. This part you've done before. You've seen the distance formula for rectangular coordinates. You've probably been told it's based on the Pythagorean theorem. You've maybe seen the proof based on the Pythagorean theorem. You all probably remember that it's hard to remember. There are square roots and squares and plus signs and minus signs in the middle of this. Let's try to do the same thing now. The formula is actually going to be maybe a little bit prettier. The distance between 2 points in polar coordinates. So let's plot this. I'll need my first part of the x-axis. This is where I'll measure the angles from, so that's going to be crucial. I don't need a y-axis for any reason. The whole point of having the polar coordinates is I don't need to think about x and y coordinates. I just need a starting place for my angle. So let's put one point here. If this is angle theta 1, then this point has coordinates r1, comma theta 1. We'll label it P1, so we can remember it's the first point. Let's make another point here. Now we'll have an angle theta 2 and a distance r2. That makes this last point r2 comma theta 2. Remember, we're always going to label our points first by the distance from the origin and then by the angle that we had to sweep through. Now how far apart are these 2 points? I can draw the line easily enough. And if this were a right triangle, it would be pretty easy. We know what to do with right triangles, but this angle is probably not a right angle. The one that I happen to draw here is pretty close to right angle, but still not precisely. What is the angle equal to? If I start here and sweep up this way, what's the angle? And I guess it's just the difference of these two angle measures. Right? If this was 30 degrees and this is 100 degrees, they must be 70 degrees apart. In particular, if this is theta 1, this is theta 2, the distance is theta 2 minus theta 1. And so I could even redraw this picture now if I wanted to. I have my angle, theta 2 minus theta 1. I have one side R1, I have another side R2, and I want to know the distance. I want to know the length of this thing here. Can we do this? Well, this could be a hard problem, or it could be an easy problem, and thinking hard probably won't be the solution. The only thing we can do here is to hope we've learned some formulas well. The Pythagorean theorem tells you the length of the hypotenuse if you have a right triangle. The version of the Pythagorean theorem that applies not to right triangles but to everything else is the law of cosines. If you remember the law of cosines, remember that you can write this down directly. If this length is called d, we'll call it this, so d is distance. We know distance squared is equal to the first side squared plus the second side squared. That's the part that looks like the Pythagorean theorem. Now we have to correct for it. We have to correct for it because it's not a right triangle. There's something else going on. So we subtract off 2 times the first side times the second side times the cosine of the angle between them. The cosine in this case is theta 2 minus theta 1. You should practice this on your own. You might even want to pause the tape right now to write down some points and practice this. But it's not too hard to do. It's maybe hard to remember, but it's pretty easy to do. Because once you have R1, R2, once you have theta 2 and theta 1, you can really just write them down. Write down the formula and find this distance. This is exciting then, right? This is powerful. Not only can we rename points, not only can we rewrite equations, but we can do some of the things that we're used to being able to do. We can do things like find the distance between 2 points. What if we want to graph? Doesn't that sound even more fun? Let's see if we can graph something. In fact, let's start with something pretty easy and work our way out. What if I want to graph, and I'm going to put our standard coordinates now so you can remember that but we're graphing something we're used to seeing. What if I wanted to graph a straight line? And this straight line goes through the origin. I want to graph this straight line. What do? Well, I have lots of different distances here. Right? Remember, our polar coordinates specify a distance and an angle for every one of the points. And certainly the distance to the origin seems to be different for all these points. But the angle's the same. Each of them I start here and sweep up the same distance. The angle is something fixed. Let's say it's equal to pi over 3. And if I write that, then I'm done here. Let's write it even bigger in celebration. Theta equals pi over 3 is exactly the name of this graph. Every point in polar coordinates whose theta coordinate is equal to pi over 3 is part of this graph, and nothing else is. What if we want a circle? Can we graph a circle? Do you remember the formula for graphing circles in rectangular coordinates? Something about square roots of some constant minus x squared and things that cause kind of confusing. Well, what are we doing here? Here, the theta values can vary. Every possible theta value is represented here. There are some things that are pi over 2 from my starting point, pi over 4 from my starting point. But everything has exactly the same distance from the origin. That, after all, is exactly how circles work. Circle centered at the origin, every radius is the same, so these all have to be equal. And so if this distance is, for example, 3, this is the x-coordinate 3, then r equals 3 is exactly what I get. My equation of a circle goes from that hard-to-remember thing with square roots and square terms to r equals 3. Isn't that great? Are you getting slightly happier? Now, here's something that works quite a bit better in polar coordinates. But there's another trick to polar coordinates. It's something we haven't talked about because it can be a little bit sneaky. And it's just this. If you start with theta equals 0, and let theta get bigger and bigger and bigger all the way until 2 pi, maybe r depends on theta in some way, then you can graph that pretty easily. But theta can keep going, right? This point here might correspond to r equals 3, theta equals 0. But it might be r equals 3, theta equals 2 pi. or maybe 4 pi, or 6 pi, or anything else. Right? There are a lot of possibilities here. There's this overlapping part. There can be lots of different r values at any given angle, because every different angle has lots of different names. These angles repeat. They're cyclic. They come back to each other. Right? We're used to seeing this on things like the unit circle, and we can take advantage of that to do something fairly interesting. How about this? What if I start here, and I want to graph r equals e to the theta? That's the same as saying theta is the natural log of r. This is something that we looked at way back when we talked about the logarithm functions and the natural logarithm function. I told you there was a way to use the natural log function to build a spiral. This is the way to build a spiral. If any theta value is equal to the natural log of r, if any r is e to the theta, and we start to plot what that looks like, what we find is it's a lovely spiral. At any point, the total distance that we've traveled is the distance from the origin is a natural log of the distance that we've traveled. And as theta gets bigger and bigger, r gets farther and farther away. It's a nice thing and it's beautiful to graph. And just like we did for parametric functions, we could graph this on your TI if we wanted to. It's much prettier on the web. I want to use this web-based software. It's free, so it's on every computer in the world. And what we do to plot something like this is simply go to Wolfram Alpha. You didn't see the last lecture. This is a wonderful online calculator to calculate things and graph things and look things up. You can see there are examples of the sort of thing that you can do if you're interested in the tide levels in Cape Town. Wolfram Alpha can tell you what they are. Right now I want to plot things and I want to do a polar coordinates plot. So I'm going to type polar plot, and I'm going to make r equal to e to the power of theta. I think this is what we did. Is that right? I'm fairly certain it should recognize this version of e. And indeed it does. If I let r go up to 3 pi, I get this picture. If I'm going to go farther, I get this. And we have a spiral that shoots out farther and farther in a nice way. It's a wonderful thing, and it's even more wonderful because how would you graph this with x and y? You can't, right? This is not in any way a function. Every y value is several different x values. Every x value is several different y values. And in fact, if we keep going long enough, there will be infinitely many. There's no hope for being able to do this nicely. And so instead we need something like this. And just like we saw for parametric equations, we can now graph things the likes of which we haven't seen before. There are several really important functions in the history of mathematics which were very hard to realize, which were very hard to generate until people started thinking about polar coordinates. Here's one called a cardioid. If you tip your head on the side and squint and use your imagination, you should think this looks kind of like a heart. Right, you see it sort of shoots up here and comes down the way hearts do. There's some ways to tweak this to make it look even a little more heart-like, but it's a mathematician's attempt to make a pretty shape. Looks like a heart and a cartoid, from cart to the same root as cardiac arrest. It's a heart shape. And it's sort of weird, right? We can maybe even imagine what's going on. Let's think about it briefly. The value of r, the distance from the origin, is 1 plus the cosine of theta. So when theta is 0, the cosine of 0 is 1. So when theta is 0, we're right here at this angle, and the r value is 1 plus 1 is 2. What happens as theta gets bigger and bigger, as theta goes up to pi? Well, what happens to cosine between 0 and pi? It gets smaller and smaller and smaller, right? By the time cosine gets to pi, cosine has a value of -1. The cosine of pi is -1. 1 plus -1 is 0. So the time I get all the way up to here, my line has shot down to be distance 0 from the origin and it starts to get bigger again. These really beautiful things happen with these shapes, things that we're not used to seeing with functions. Here's another one that's been popular both historically and is still sort of nice to make a picture we like to see. Its proper name is a lemniscate, but I think if you look at it, it will look like something else to you. If we use r squared as 4 times the cosine of 2 theta, we get a picture that looks just like this. Just one of these is all we need. A lemniscate is an infinity symbol. We can graph it now. We can graph infinity symbols. If mathematics is worth nothing else, isn't this great? Isn't this what we can do? And imagine what you can do when you tweak these things. As I did for parametric equations, I strongly urge you to spend time experimenting, to spend time literally playing around with this and seeing what you can do. You can do wonderful things. I want to show you one more. This one was actually discovered by a pre-calculus student. The pre-calculus text that we use at Central was written by a guy named Cohen. And every year he asks his students to play around and try to make pretty pictures. And one of his students, whose name embarrassingly I can't remember at the moment, but check his book if you want to know, came up with this. Oscar something. It's called Oscar because this is called Oscar's butterfly. Alright, you ready? Isn't that great? Can you imagine there's an easy function that you can graph to do this? It can't be a function where y is a function of x, but it is certainly a function where r depends on theta. There's much we can do, which is first of all just fun to play around with, but again I'll remind you, incredibly useful. Everything that goes in circles, every planet, every wheel of a car, every motor that spins, every hard drive that rotates, all of these things, to be carefully described, need polar coordinates to do it well. It behooves us to learn them, and to learn them now. So with this, I leave you, and thank you.